Welcome back to the Hyperbolic Coding Chamber. This is day 62 of Daily LeetCode. Daily LeetCode, Daily LeetCode. So we are back once again with a W comment from Thomas himself. Trapping rainwater, you can do monotonic stack. I have no idea what a monotonic stack actually means, so we're going to have to do some research upon that. Also, probably going to be doing a shorter session today, but more problems to be done. We're still slacking on evaluate division. We're supposed to mock this contest, which we still haven't gotten a chance to. There's a long backlog. We also want to do some of Don Martin's system design, but I'm going to have to pass on that today. Sometimes you got to walk to run. So day 62, we have balanced binary tree to do. And I think this one, balanced binary tree, I think we did this one yesterday and I forgot to update it. Oh, no, we didn't do this one yet. So we have to do balanced binary tree, and we're gonna do some random problems. And yeah, we're still stuck on evaluate division. Actually, we're gonna do balanced binary tree and the rest of the time on evaluate division because I keep putting it off. So we're gonna do evaluate division and then balanced binary tree. And then, yeah, that would be it for today. So we're gonna try for an hour, but we shall see. So balanced binary tree and then evaluate division. And then, yeah, we'll see how far we get with those two. And also, yeah, if you're doing something similar, or if you're working on something similar, or if you have some cool tips to drop like Thomas, you let us in on the monotonic stack cheat code. I still have to learn what that is, but if it's possible, it would be pretty dope to be using on this problem. But I'm also hoping the algorithm design manual also shows us another way to do this problem, but I'm hoping it also touches on the monotonic stack. So thank you for the infinite cheat codes again, brother. So I'm hoping the ADM lets us in on this because we have a lot to learn. So we'll try balanced binary tree, then evaluate division, and then, yeah, also don't forget to join the HCC, right? Lots of cheat codes, infinite cheat codes for your technical interviews. So yeah, a lot of cool tips and tricks in there on how to bomb your next technical interview. So you're gonna wanna join to figure out how to do that. And then, yeah, we'll see if we can explain some problems today. And yeah, let me know if this helps or if my teaching method is subpar, and we can make it better. So just gonna jump into it so I actually plan to do 45 minutes, but we're just gonna do balanced binary tree. We'll do one random problem and then we'll do evaluate division. So balanced binary tree. Given a binary tree, determine if it is height balanced. Right, for this problem, a height balanced binary tree is defined as a binary tree in which the left and right subtrees of every node differ in height by no more than 1. Right, so in this case, look at the subtree of the left subtree, right? Its height is 1 of the left subtree, and the height of the right subtree of the root node is 2, right? The difference is 1, so we're fine. In this case, the height is 1, and in this case, the height is 3. So the difference is 2, which means that they're not height balanced. So interesting. I think we've solved this one before with a function that looks like a BFS, right? So we do a BFS, right? And then as we get the root node, right, we start with 3, right? And then from there, we actually do a DFS for both the left subtree and the right subtree to calculate their heights. And then we actually do that for every node in the tree. So I think worst case, that's actually n squared. Actually n squared time complexity, I think. It's because we're doing the BFS, which is going to visit every node. And then for each node, we're going to call 2 calls of our DFS, which is also going to visit pretty much, at worst case, every node in the tree if we start from the top. So that's going to be n squared. Wondering if we can come up with an O of n version, which I think is definitely possible with the DFS based approach, but I wonder Actually, no, I don't think there's an O of n solution. I think there's another solution I remember reading where it was like you do a DFS onto the farthest node you can get, which would be 7. And on your way up, right, you're at 20, right? And then you just simply do you would check the height of both of these trees, right, to make sure they're not different. I mean, their difference isn't too large. And if their difference isn't too large, if it's not greater than 1, then that is where you would, if the difference is greater than 1, then that's would be a problem. So you would return false because it wouldn't be balanced. All right, but then you end up at 3, do the same thing. So I think actually both of these solutions, DFS solution I think is still n squared, right? Because at each point in the tree, right, you still have to call, right, this function which calculates the height. I don't know if I'm seeing a version that's possible with n squared. So this array, this representation of this binary tree looks like 1, 2, 2, right? Which means that the next 2 nodes would actually be 3, 3, right? Which means the next, so if we have 1, right, left subtree would be 2, right? And from there we would go, we would hop 1 node to get 3 and then we actually hop 2 nodes to get to 3. We can hop another 2 nodes to get to 4. Wondering if there's a way, if you generate the array, to tell whether or not the array to be able to tell if you could generate this array, right, which you could, of nodes, there's a way to tell from that array that it is not height balanced. So if we were to break these up into groups, right, you have the root node, then the 2 children, right, then the root node, then the 2 children. Or, oh no, within these, then we have the 2 children of the left node, right, and the 2 children of the right node, right, which is still null null, the 2 children of the left node. Whereas if you look at it like this, for the balance tree, right, we'd have this to start, 2 children, So to break these up, we'd have 1, 2, 3, 4. 4 groups, which means you have 1, 2, 3, 4. So that's interesting. Whereas this one has a total of 3 groups of elements. Does it make sense that for n, if we were to generate the array, does it make sense that, for example, the number of pairs of 2s after the first pair of 3, if it's even, Well, additionally, we know that if the root doesn't exist based on example 3, right, then we should return true. There's got to be a version that's not. n squared, I guess trying to find a linear time solution. If 3, is there a way to visit, is it even possible to do this in one go? There's no way, because if you're going all the way down the tree, and you need to make sure it's not, that it's height balanced, right? There's at least with the DFS, maybe the best we can do for this is n squared. So maybe that's what we'll go for, right? And the intuition for that is just that we'll go a level order traversal. And for each node that we process, we'll calculate the height of its left subtree and its right subtree. And if it's too great, if the difference, if the absolute value of the difference is greater than 1, then we want to return false, right? So we'll do an LOT, we'll do DFS, right? 1, right? DFS 2, right? And we'll say if DFS 1, right, minus DFS 1 minus DFS 2, right, is greater than 1, we want to return false. Otherwise, we can return true down here. So to do that level order traversal, we'll use a queue, right, with the root to start. We'll say while the queue, right, still has values, right? So while the queue dot length is not equal 0, right, then we're going to have to process these heights, right? And so to do that, we can just say const h1 is equal to the height of, right? So we also want to make sure we get, we're going too fast. Level order traversal, we want to pull, right, the current node off of the queue, right? We've already made sure that it does exist, because if not root, right, we return true. So we know that root does exist. And here we want to say cur is equal to q dot shift. And we'll say if cur exists, right, if it's a value that does exist. And actually we can guarantee that it exists because of this if case up here. So cur will exist, and we'll calculate the height, right, of cur dot left, the height of cur dot right. And then from here, what we're going to say is if math.absolute value of h1 and h2 is greater than 1, we want to return false, just like the code down here says. And then additionally, right, if cur.left exists, right, then we're going to want to push it onto the queue to be processed next. Then we're going to do the same for cur.right. Now what remains is to implement the height function. This is going to be a depth first search-based height function, which is going to take a node, which is going to be a tree node, or null, which returns a number, right? And we'll say the node has to exist, right, to give us a value to return. Otherwise, we're going to return 0. Right, and so to calculate the height, right, all you have to do is, like, let's say we're starting at node 3, right? 3 does exist, right? And what we actually want is the height is actually going to be the pretty much the deepest depth of both the left subtree and the right subtree. So always going to have to check which one is deeper between left and right. So to do that, we're going to have to return the math.max, right, of height of node.left and height of node.right. And then we can add 1 to it, right? Because the root node also counts as well, right? So from there, right, what we'll do is we'll say, okay, get the math.max of height node left. So we go left, right, and then node 9 does exist. So then we have to get the max height of its left and right subtrees. Well, neither of them exist. We return 0 and 0. The max of 0 and 0 is 0. Plus 1 is 1, right? And then we go up to 3. Now we have 1 here for this height. Now what do we get for this right-hand side? Well, 20 exists, right? Those 20 exists, we're gonna do return 1 plus the math.max of left and right. These are both gonna return 1. We're gonna add 1 to 20 to return 2. So now at 3, we're gonna be taking the max of 1 or 2 and adding 1 to it. So we're gonna return 3. Right, well, we're actually calling this with 9 and 20. So you can see we pull the cur off the queue, and then we actually do height for left and right. So we're actually gonna get 1 and 2 respectively, which we take the difference of, right? So we should be good here. But I'm pretty sure this is how this one is n log n. You know, for this one, next time we see balanced binary tree, now that we know a linear time solution exists, right, I think we'll just aim for linear time. I see. So it uses this method to visit every node. Okay, I think we can implement this next time. I think we can do this in linear time. But earlier we said it wasn't possible to do this in linear time because I didn't know you could just, with the way they're propagating up the tree, right? When you get up to this node, you've already counted both. That's a clever way to do it. So we're back with evaluate division. So if we're given an array of variable pairs, equations, and an array of real numbers, values, where equation sub I is equal to a sub I, b sub I, and values sub I represent the equation a sub I divided by b sub I equals values sub I. Each a sub I or b sub I is a string that represents a single variable. We're getting some queries where query sub j is equal to c sub j, d sub j. Represents the jth query where you must find the answer for c sub j divided by d sub j equals question mark. Send the answers to all queries. Answer cannot be determined, return -1. Input is always valid. You may assume that validating the queries will not result. In division by 0, that there is no contradiction. So let's map this statement. Let's map the problem statement to our example. Give an array of variable pairs equations. So we have equations a, b, b, c. An array of real numbers values, or equation sub I. Where values where equation sub I is equal to a sub I. Equation sub I is equal to a sub I, comma b sub I. Okay. And values I represent the equation a sub I divided by b sub I. They're saying that we're given a bunch of equations, right? A, B, B, C. And they're saying that A divided by B equals values, and B divided by C equals 3. There's some queries where C sub j is equal to D sub j, represents the jth query. C sub j, comma D sub j represents the jth query, where you must find the answer for C sub j divided. So you have to find the answer for A divided by C, B divided by A, and A divided by E. Find the answers to all queries. If a single answer cannot be determined, return -1. So they return for x divided by x, they return -1 since x wasn't given to us as a possible solve for in terms of values and equations. Input is always valid. You may assume that evaluating the query will not result in the first. So we know that this is solvable. The hint says, do you recognize this as a graph problem? Related topics are array, depth first search, breadth first search, union, find graph, shortest path. So I guess they're saying that A divided by B, right, gives us 2.0, right? And they're saying that B divided by C gives us 3.0. Somehow I need to figure out what A divided by C is. A, E, A, X, X. E doesn't even exist. Okay, so they do return -1 for this because E doesn't even exist. A divided by B equals 2.0. B divided by C equals 3.0. A comma C, B comma A. It's even possible for multiple equations and multiple variables. B, C, I guess this means multiplication. Equations. This is a simple example. You know that A divided by B equals 0.5. And their queries are A divided by B equals 0.5. B divided by A B divided by A Two divided by 2 is 1. 2 divided by 1, 2. So if we have A divided by B equals 0.5, and then when B divided by A equals 2.0, by 2. Out of without creating some way to parse equations and solve it, I'm not seeing how this is possible. A divided by B equals 2, and then B divided by C equals 3. If we try a simpler version, right, so A divided by B equals 0.5, so what they give us, right, and then B divided by, what they want is A divided by B equals 0.5, right, and then B divided by A equals 2.0, and then also have A divided by C equals -1, X divided by Y equals -1. So you know that if letter doesn't exist in equations, right, then we will turn -1 for a query. So if letter doesn't exist in the equation, right, then we want to return -1 for query. AB, so we have A divided by B. A divided by B equals 0.5, and the query's A divided by B, which means maybe we need a way, other than having a map to resolve A equal to certain some value and B equal to certain some value. We have B divided by A. And then A divided by C. How could you figure out that A divided by B equals 0.5 just with the values here? What if we take A and B and we find the next case that has both variables, right, B and A? We know that that outcome is 2, right? So we'll find the next one, right, with the edges reversed, right, we'd have 2. A divided by B, B divided by A. What if that's not possible? In this, only have equations A, B. Is there another one in here that's BA? BA isn't even in here. In terms of the queries, so BA doesn't even exist. Maybe there's one for, say, BC. Is there one for CB? There is. Maybe that's something that's static. We have AB. Do they have BA? We do. Maybe that's something we can use to parse or figure out the first value of the variables. So if we have A, right, let's just say we find we'll say we'll just find the reciprocal in queries, right? That would be B over A equals. I'm just realizing now we actually have no idea what those values are. So we actually don't even know that it equals 2. What if we know, all right, that A over B equals, A over B exists. That A over B exists, and we can rewrite it as B is equal to A times 0.5. Equals A times 0.5, then if you could swap in A divided by A times 0.5, that doesn't make any sense. So if we have A divided by B, what we want to solve for in our equation is actually, I'm going to solve for A. To do that, we just multiply A over B times 1 over A. We get A is equal to 0.5 over B. Maybe there's some uniform like trans. Well, this is actually not true. So I think we should use our simple example. We know that with AB, we're able to figure out. We know with AB that we can get to 0.5. So we shouldn't need to find the reciprocal in queries. We'll say find in So what if we take a different one? right? We don't need anything more in equations, maybe we just need things that exist in queries. So we have A comma B. What if we do something with B comma A? Like we set up here, right? We're doing something with B over A, so what if we solve for A? All right, that would mean that A is equal to B 0.5, B times 0.5. We have A over B equals 0.5. Then A is, you solved for A, right, which would be the first variable in this division, right? One of our queries is B divided by A. Then maybe if it works out like this, you can always just swap in B 0.5 B divided by B would be equal to have B of 0.5. Have B of 0. Or B, that doesn't quite make any sense. We divided both sides by 0.5. One over 0.5, which would be equal to 2. So is B equal to 2? Let's say B is equal to 2, right? And A is equal to 1. 1 over 2 is 0.5. Okay, what about 2 over 1 is 2. So maybe this is the plan, right? If you have A over B, right, you find the query, right? We have to just be able to know if there's another one where B is divisible by A, right? And if we do that, let A is equal to B times 0.5, then we swap it in with this, and we pretty much will divide B by the value 1 over 0.5. Which is we could probably repeat this over and over again. So let's just say if we had, now that we know that b is equal, so we have a divided by b, what we can figure out is what b is. A divided by b, we can figure out what b is. We can figure out b, okay? If we can figure out b, how do you do that? Right, you have a divided by b equals 0.5. Right, check if b over a exists. If so, right, then we say that b is equal to 1 over 0.5. Which means b is equal to 2. All right, now that we know that b is equal to 2, now we need to figure out what a is, right? But if a is, now we need to figure out a. Now if we know that a exists, maybe, all right, we know that now that a over 2 now we know that a over 2 equals 0.5. Which means that a is equal to b times a over b. So if we do, it should mean that a is equal to 4. So we do if we do 4 divided by 2, we get a is equal to 4. And we do 4 divided by 2, then we get 2, which is off. If a divided by b, then we can figure, I think we messed this up. A divided by b, we can figure out a. Let's check if b over a exists. A over b, we can figure out a. Previously it said we can figure out b. A over b equals 0.5. B over a does exist, right? that's the case, then we can set it equal to zero 0.5 over a. Then if we plug it back into plug back into 1, you should get a divided by 0 0.5 where a equals 0 0.5. That's definitely not how you do it. Maybe we're looking, I think the way this problem works is you need to figure out some basic equation like division stuff, and then you can take it through its paces with the graphs. I think we need to read on how to solve equations. I think I'm realizing that's what the bottleneck for this problem is. The way I'm going about solving the equations doesn't make any sense. So a self-referencing nature to equations that pairs well with graphs. I'm just not seeing how we get from A comma B. Even if you model it as a graph, we'd have A comma B. think there's, if I delete all this and go back to the beginning, we have a over b equals 0.5, b over a equals question mark. Should be able to figure out at least the answer to one of these values. And divided by b equals 0.5. To figure this out, we'd have to example, if you had let's say a equals 2 and b equals 1, or a equals 1, b equals 2, a over b would be 0.5, and then b over a would be what? A over b times 2, which would be 1. For b equals 1, and b over a would be equal, in this example, would be equal to 2. So if a over b equals 0.5, and b over a equals 2, twice of that. Let's see if that makes sense. If a over b equals 3.75, so we have a. B over a we don't, we have a b and c. Let's say b and c equals 0.4. No, b and c equals 2.5, right? So when we have 2.5, when we have c and b, right, the answer is not 5. Yeah, I don't get this one. As reviewed by Harris, the problem can be solved with 2 important data structures, graph and union find. In the following sections, explain how to solve the respective reports data structures. First, let's look at the example given the problem description. Given 2 equations, namely a over b equals 2, b over c equals 3, we derive the following equations. B over a is equal to 1 over 2, and c over b is equal to 1 over 3. A over c is equal to a over b times b over c, which is equal to 2 times 3. Huh? B over a over b is equal to, oh, I see. I was going for like a over b plus b over a. Whereas they're giving us A over B and B over C. So I was trying to use queries, but queries actually doesn't even matter. So with that hint, let's try and figure this out. If A over B equals 0.5 and B over C, A over B gives us, actually let's go over them. Maybe this is possible now, knowing that we can now do A over B going to B over C. So I'll return tomorrow